We're going to take a look at 2023 AP Physics 1 free response question number 1. A cart on a horizontal surface is attached to a spring. The other end of the spring is attached to a wall. The cart is initially held at rest as shown in figure 1. When the cart is released, the system consisting of the cart and spring oscillates between positions plus L and negative L. Figure 2 shows the kinetic energy of the cart spring system as a function of the system's potential energy, and friction forces are negligible. On the graph of kinetic energy K versus potential energy U, shown in figure 2, the values for the x-intercept and y-intercept are the same. So this and this are the same. Briefly explain why this is true using physics principles. So to solve this question, first, let's talk about the conservation of energy. This principle tells us that the energy can't be created or destroyed, it just changes form. In our system, the energy switches between kinetic energy, or the energy of motion, and potential energy, or the energy stored in the spring. Because friction is negligible here, no energy is lost to heat, meaning the total mechanical energy stays constant throughout the motion. Now let's look at the graph. This graph shows a straight line relationship between kinetic energy and potential energy. This linear relationship indicates that as the potential energy increases, the kinetic energy decreases by the same amount and vice versa, keeping the total energy constant. When U is 0, all of the energy is kinetic. So at this point, kinetic energy equals the total mechanical energy. And from the graph, this maximum kinetic energy is 4 joules. When K is 0, all of the energy is potential. So here, at this point, potential energy equals to the total mechanical energy. And again, from the graph, the maximum potential energy is also 4 joules. Why are these intercept values the same? Again, it all comes down to the conservation of energy. The total mechanical energy of the system is 4 joules. So this value remains constant, whether it's in the form of kinetic energy or potential energy. So this was part A. Next part says, when the cart is at plus L here and momentarily at rest, a block is dropped onto the cart, as shown in figure 3. The block sticks to the cart and the block cart spring system continues to oscillate between negative L and positive L. The masses of the cart and the block are m0 and 3m0 respectively. The frequency of oscillation before the block is dropped onto the cart is f1. The frequency of oscillation after the block is dropped on the cart is f2. Calculate the numerical value of the ratio f2 over f1. Okay, so we know the formula for f is 1 over 2 pi square root of k over m. We want to find f2 over f1. So this is 1 over 2 pi square root of k over m2 divided by 1 over 2 pi square root of k over m1. So f2 over f1 is equal to square root of m1 over m2. So m1 is the mass of the system before the block is added, so it's only m0. So this is equal to m0. And m2 is the mass of the system after the block is added. So it's m0 plus 3m0. So it's 4m0. And this is equal to square root of 1 over 4 or 1 over 2. Part C. The dashed line in figure 4 shows the kinetic energy K versus potential energy U of the block cart spring system after the block is dropped onto the cart. This graph is identical to the graph shown in figure 2 for the cart spring system before the block is dropped onto the cart. So briefly explain why the two graphs must be the same using physics principles. If we look at this part of the question again, we see that the second block is added to the system when the system is at rest. So it does not have a kinetic energy and only has a potential energy. We know that the formula for the potential energy is 1 over 2k x squared, where k is the spring constant and x is the displacement from the equilibrium position. This formula is independent of the mass of the system. Therefore, changing the mass of the system does not affect the potential energy stored in the spring. So the graphs must be the same because of the principle of energy conservation. In both cases, before and after the block is dropped on the cart, the total mechanical energy of the system is conserved, and it is the sum of the kinetic energy K and the potential energy U at each point. The second part of this question says, after the block is dropped onto the cart, consider a system that consists only of the cart and the spring. So forget about the block, only cart and the spring. On figure 4, sketch a solid line that shows the kinetic energy of the system that consists of the cart and the spring, but not the block after the block is dropped on the cart. So the maximum potential energy here stays the same. It's still 4 joules. What we need to find to be able to draw this graph is to find the maximum kinetic energy for the cart and spring system. So we know that the potential energy of the block, cart, and spring system is 1 over 2 m2 v squared, and it is 4 joules. What is m2? It's 1 over 2 4 m0 v squared equals to 4 joules. If we cancel this 2, we have 1 over 2 m0 v squared equals 1. And this is the kinetic energy of only the cart and spring system. So the kinetic energy of only the cart and spring system is 1 joule. So now that we know this, we can draw the graph. We need to connect 1 to 4